All right, am I live? Can you guys hear me? Okay, we're live. Let me do a quick mic check. Hello? Uh, yep, that's the mic check. We're good. Okay. Hello and welcome to another live stream. It's been a while since my last live stream, so let's hope this goes well. Sorry for the delays. I thought I was live. I kind of forgot how to use the live uh, stream settings here. All right, well, let's get into it. So on this live stream, I'm going to review the code here for uh, Revenge. Let me check that. Let me confirm that the video quality is actually good because it is code, and I will need to maybe zoom in a bit to get it to be more readable, maybe. Okay, it is readable, but a bit more zoom, I believe, would be better. So let me just zoom in a bit. Okay, and that's that. So what is Revenge? Revenge is a bunch of tools, I believe. One being the compiler, which means that it takes a binary and then what it does is that it turns binary to C code. And that is called decompiling. It does that using LLVM. What it does is that it turns the code to LLVM IR and then tries to lift LLVM IR to C code. So uh, it is it is partly open sourced. So today I'm going to read and review part of the open source code. Uh, there's a bit of good documentation out there for it on the Git. You can go and check the Git from their website, and uh, it it should get you going. But sometimes you need a bit more help than the Git itself, and you have that than the documentation itself, and you have to sometimes do some guesswork to get it working. So I've got it working. I have the Git here. It uses Orchestra for build system and all of that package management. Which this was the first time I was encountering Orchestra, and it looked really fine for me. I enjoyed it. And if you have ever tried to kind of like write a pass for LLVM, you will see that it is not that easy to get uh, out of what is the exact terminology? I don't remember it right now, but there is a terminology that is out of source pass, that you build your pass outside of LLVM structure, and then you compile it to a binary, to a library, to a shared library, and you load that shared library into LLVM as an optimization pass or as some kind of pass. Doesn't need to be optimization. Uh, it is kind of difficult to deal with the build system of LLVM. So I believe that is why they are using Orchestra, which makes it fairly simple. So with all that said, let's get to my setup here. I am on a Windows machine, but I'm using WSL. WSL is just Windows subsystem for Linux. So it's kind of a Linux kernel running on Windows. And I am today trying to review part of their code that is a pass that is called function isolation. So if I want to give you a quick introduction on how Revenge lifts code from binary, is that it tries to emulate the binary inside LLVM IR with using LLVM IR. So it generates an LLVM IR code that emulates all the registers, all the memory, and then what it does is that through that emulation, it is able to run your binary inside LLVM IR. So, and then it tries to lift that LLVM IR into an actual code. So this emulation means that first they have like literally they are dealing with registers that are declared as variables, as global variables. These are all documented on their websites, on their GitHub, so you can go and see the documents as well. Uh, so yeah, what then later it does is try to make sense of that emulated code. So for example, function calls are emulated as jumps, and they need this pass called isolate function that we're going to review today to detect those jumps and their companion instructions like manipulating the PC register, manipulating the saving the frame pointer, stack pointer onto stack, and those kind of epilogues for an actual call. This pass tries to detect those epilogues, those companion instructions that comes with jumps that are actually function calls. It tries to detect those, and then it is going to try to make actual function calls from those. So there's a bit of documentation that you need to go through to maybe understand it completely, like how all the things work. You can find it on their website. It is fairly accessible on their GitHub, and their GitHub is available through their website, and the link to their website is on the description. So make sure to give a visit. All right, let's go to the code here. I've collapsed everything here. This is the actual module, the pass that is registered to LLVM. It is fairly similar. Sorry, fairly similar to the LLVM stuff, LLVM modules that you would develop, LLVM passes. I think they're actually using the same thing, that they're actually registering LLVM passes here. These are literally LLVM passes. So yeah. So let's get to the code and see what it's actually doing. This is fairly the first time I am seeing the code as well. So I'm trying to make sense with you guys here. Uh, Here we have the register pass here. That is the exact thing that we get in an LLVM pass. So I believe this is an LLVM function. Yeah, the structure LLVM register pass registers a pass. What pass we're registering? It is called IF here. And what is IF? It's a simple structure here. Let me bring up the code. Let me close some of these files that we don't need it right now. All right, with all that gone, let's go and see what IF is actually. All right, so this is a module pass here. As you can see, LLVM module pass. It's called isolate function. Has an ID here that passes it to it. And first thing that comes to my mind, I believe they're using C++20. I'm not sure about that, how much of C++20 their compiler supports. I'm gonna open up a note here and save this as, okay, where do I save this? Here. I'm gonna save it as notes.txt. Okay, not .txt, maybe MD5. Okay. So one thing that I've noticed is this ID that is static char that will require them to come and declare it other than definition here. They've specifically declared it in their CPP file. That can be made inline variable. I prefer inline here. So let's have that noted here. Isolate function.h and then when I'm going line 16, make ID inline. These are suggestions. These are not really required to be actually done to the code. Like this is an extra comment, so you probably will not change your ID to inline because it is simply working well right now. So there's no need, but I would prefer it to be inline. So that would remove this line of code here that someone sees and it comes to their mind. What does that actually mean? And so they're registering these isolate functions. So I have a bit of cough, so you will hear me coughing throughout this stream. And yeah, okay. So they're registering this pass that is called isolate functions. It has a constructor that does nothing but construct the module pass from LLVM. Then there is this run on the module, which we're going to take a look at. And then there is this get analysis usage. What does this do? Set preserve all. Sorry. Set preserve all. Add required. Generate code basic information wrapper pass. Load module wrapper pass. So I believe what this does is tell LLVM where to actually use this module. So it is saying that probably these two passes should be run before isolate functions is run. I believe that is what that is, but let's take a quick look at the actual documentation of LLVM. And let me do a quick check on the stream quality as well. Seems to be fine. All right. LLVM analysis usage information. Sorry for not sharing the my search results here because I'm just sharing the Visual Studio. I need some kind of a stream deck or stuff like that to get this working, get my streams a better quality. So let's see. Get required set, add required. There is not much of good present analysis usage information of a pass. More. The track analyzes the tracks analyzes that the pass must be available when the pass runs. Requires transitive must be available throughout the lifetime of the pass, and the analysis that the pass preserves the pass does not invalidate the results of these analysis. Okay, I think I got the gist of it. So what this preserve all says is that running this pass will not deprecate any result of any other passes that have been run before. And these requires are telling the LLVM that these passes should be run before running this pass. All right. I hope that makes sense. So now let's go and take a look at this run on module, because the rest of this we've covered so far. Okay, let's do that. Let's come here to this run on the module. So what does this do? Get analysis, generate class basic info wrapper pass. So this gets this pass off of analysis, and then another pass here that is called load module wrapper pass. I have no clue what that is. And why is this not const? That's something to think about. And then we have this binary module wrapper and binary module wrapper here. What does this do? Module wrapper, get read-only model. That's interesting. And what is this model? Namespace model, binary. We will take a look at this later. I'm just gonna DFS on this. All right, so what this does then is construct an IFI here. That is another structure that is defined above, and then it just constructs it and calls the run. Let's go to the constructor here and let's see what arguments is passed to the constructor here. The module get function, so it is getting the root function from the module that is being passed to us as a pass. So this is the root function that emulates all the things that has been recovered from the binary. And then there is this CGBI pass here, which I have no clue what that is. And then there is this binary that is get read only model. I have no clue what that is either. So this is using the load module wrapper pass, and this is generate code basic info wrapper pass. I have no clue what these are. But let's take a look at the constructor of this IFI. Not here, I'm looking for constructor. Okay, the class is declared here. So here we have root function. So we know what root function is, but why is this passed as a pointer? I don't know. I would rather it was a reference rather than pointer. So let's go on. As you can see, we are holding a pointer here as well. I doubt the code would work if root function is null pointer. So if root function has to exist, this better be a reference than a pointer. So let's take a look at the usage of this root function and see if on any of these usages we have, okay, yeah, right here. You can see that root function cannot be a null pointer because if it was a null pointer, this is a null pointer dereference, and we are in undefined behavior here. So I'm just gonna do a quick note on this. Isolate functions .cpp line 146 make function a reference. All right. So so far it is just it's just initializing some variables here. Sorry for that. And why are these not initialized at all? We will later figure that out. Sorry for my coughing here. I kind of have a cough, so yeah, sorry for that. And all right, then we're just initializing these. A root function here is initialized. The module is initialized from get parent. Okay, and what about you actually pass the module first and then you get the function? I don't know. Then from the module, they're getting the context. I have no clue what context is. It is LLVM context, and it is a reference here, interestingly. Then we have GCBI, which I have no clue, generate code, basic info. And then we have binary, which again, I have no clue of. And then we have strings, the module. What is that? Constant string pool. Let's see what this is. It has a module inside it. Then there is this string pool, which is a map from a string to global variables. And then let's see. When we have get, it takes a string What? The concatenation of temporary values has strings. The twine is kind of rope. It represents the concatenated string from arbitrary, from from a binary tree where the string is pre-ordered of the nodes. Pre-order of the nodes. Interesting. What does that mean? Mm. Particularly in cases when the twine result is never required. What am I reading here? Let me just select some of these so you can read with me as well. Since the twine can be efficiently rendered into a buffer when its result is used, it avoids the cost of generating temporary values for intermediate string results, particularly in cases when the twine result is never required. By explicitly tracking the type of leaf nodes, we can also avoid the creation of temporary strings for convergence operations, such as appending an integer to a string. Twine is not intended for use directly and should not be stored. Its implementation relies on the ability to store pointers to temporary stack objects, which may be deallocated at the end of this statement. Twine should only be used accepted as const reference in arguments. All right, I have no clue what twine is here. That did not help me at all. But yeah, there is this twine name. Where is it used? It's not used at all. What is twine? I have no clue. Okay, let's see what this constant string pool is. Just has a get that returns a constant, and I believe this is LLVM constant. This is an important base in LLVM. It provides the common facilities of all constant values in an LLVM program. A constant is a value that is immutable at runtime. Functions are constants because their address is immutable. Same with global variables. So yeah, I guess I understand what constant is. It's probably a node of their IR that defines something, some value that is not going to be changed. It's a constant value. All right, so we're getting the constant value here. There's a string and then there's a name that is twine. And then what is going on here? Auto it iteration iterator string pool find string. So it finds the string here from our string pool, but who initialized our string pool? I have no clue who initialized it. Ah, okay, probably it's initialized here. Auto C get context, so we're getting the context of the LLVM again here. That is called C, and then we're checking if we have actually find our string inside our string pool. We simply do here. We come here. If we find our iterator, we come here. What we do is get int atyc. What does that mean? Get pointer to. And then let's see what this is. LLVM type get int 8ty. So I believe this is get int 8 type from C, get pointer to. So this is a type, I believe. And then what we do here is we get pointer cast here from iterator second, that is pointer to global variable, I believe. And then we pointer type, we cast this to pointer to unit 8 pointer. All right, I think I understand what is going on here. We're getting the address of our global variable and we pass it as a pointer to unit 8 type here. Okay, but what if this string does not actually exist? Then what do? We come here, constant data array, get a string. What is a constant data array? An array constant whose element type is simple 1, 2, 4, 8, byte integer for floating double, and whose elements are just simple data values. Right? Get a string. This method constructs a CDS and initializes it with a text string. The default behavior at null true causes a null terminator to be placed. So, so this is generating some kind of constant for us. And what it does is it takes our string here and then it turns it into a constant for us, and it adds a null termination here as well. So we have this constant here, and then we generate a global variable from that constant. And this is our module. Then new global variable, get type. Then what are the arguments here? Module type is constant, which is set to true. Linkage type is internal linkage, so it's kind of static. So we're kind of declaring a global static variable here. And then there is the initializer that we say that we have this global variable that is constant, it is static, and this is the initial value. So this is the initial value that is a constant here. And then we just insert this new global variable to our list of maps. So list of global variables, this map of global variables. But I have no clue what this name is, what it was supposed to do, and why it exists. So I have no clue. Other than that, this seems all right. And we're constructing a global variable using a string, and oh no. We're inserting with a hint here. This is an insert with hint because we have done the find. So we're hinting that it doesn't exist. And then we have this pair that is going to initialize. I think this could be an in place rather than insert. Would be better. I don't know. Anyway, so we got what this is doing. This is constant string pool. It just declares some kind of global variables for us and puts them in a map that we can access them whenever we want. So this is kind of holding our constant strings. All right, I can deal with that. Let's close this. And I believe we needed the module here that is passed on the constructor to this to make our global variables. We're saying that our global variables are for this module. Okay. All right, then let's go back to our code here. So that is this constant string pool. But yeah, strings. Then we have this exception source PC global variable. There are two global variables here that are probably going to be initialized inside this run function maybe. All right. I think that is our constructor here. We will have to take a look later to see what these are: raise exception, function dispatcher, and call maker. I believe these are going to be get from our module here, but I have no clue why they haven't been initialized in the constructor while they could be. Let's see where these are actually initialized. It is the usage here, and why could it be null in the first place? I have no clue why that is. TY create. So no, it is created. Created, replace call maker run. Okay, we are on the run now. Let's read the run function of the implementation of isolate functions. So what it does at the beginning is exception source PC and create struct variable the module exception source PC. Why did we not do this at the constructor? Create a global variable with meta address type. String reference module. No clue what this does. Create a global variable with meta address type. What is meta address type? I have no clue. So create structure again. We have the same kind of function called with another kind of name. Exception destination PC. So this is exception source PC, and then there's exception destinations PC. I believe create a meta address type. I have no clue. Literally no clue what this does, but I'm assuming it is declaring some kind of variable with the name here, which is of type pointer, and that is what the name suggests here as well. So yeah, all right. Then there's this args type here. What is the args type? Value of vector of types. Declare the raise exception helper function that you will use as a throw. So let me just give you a bit of background on what this, why we are starting with raising exceptions right off the bat, like what is going on. So there is this dispatcher, because as I said, every single call is translated to a jump function first, jump call first. So there's a jump instruction there for each call instruction. And then what happens to decide to actually where to jump, because usually on the code you see jumps that are to addresses, to specific addresses on the binary. But here you don't have any addresses on LLVM IR, you have just a bunch of labels. So what happens is that when you try to actually jump somewhere, you call this dispatcher function. So when you read somewhere that is mentioned, whenever you see a mention of dispatcher, here you can see the dispatcher. It is, what it does is to map one of those addresses to the beginning of a basic block. So the basic block on LLVM is a block that is a block of instructions, a set of instructions that are that's just a simple list of instructions that do not have any jump in them. So yeah, so when you want to actually jump somewhere, some address in the code, you are calling the dispatcher and telling the dispatcher that this is the address that I want to go. Then the dispatcher has the responsibility to map your address to the beginning of a basic block and then jump there. So that is what the dispatcher does. Dispatcher just maps your address to a proper basic block. Then when you want to do a function call, you just call the dispatcher, give it the address, and then you jump there. And you at the beginning you only have a single function that is called the root function. Later, what this module is going to do is going to isolate some other functions. And if you're on other function, you cannot jump into some address that is in some other function. That is just how LLVM works. It doesn't let you to jump from one function to another function. You have to do proper call. And that is when the problem arises. You have this dispatcher that you were calling, you were jumping to, but the dispatcher may result in a jump that is in some other function. So the LLVM is not going to allow you to do that. So what happens is that they use exceptions to rewind the stack, get out of the function, get to the dispatcher, and then do the proper call there and get back. So that is why we are seeing exceptions here. Anyways, these are all documented on their documentation on their GitHub. You can go and read on those later. But yeah, that is what I understand so far. I don't have a deep understanding of this concept either. So yeah, I'm just trying to read the code and understand it. I have read just as much as the documentation had provided me. Anyways, so that is why we are doing these exceptions here. This is exception source PC, exception destination PC. I'm assuming these are to handle exceptions. So this is where you trigger the exception, you throw the exception, and this is where you want to get to when you're throwing the exception. All right. So these are these args type. So what I'm assuming these args type is the type of the argument that you pass in the function when you're trying to raise the exception to get to that function. So function that we'll use as a throw. Declare the raise exception helper function. Okay. So these arguments are these are the type of the arguments for raise exception helper. We're creating a function here that is called raise exception. And what arguments does that take? It takes a pointer to int 8. I have no clue why int 8. Then there's this the type of the source PC and destination PC. So when you want to raise an exception, you probably are going to call this raise exception function, and then you will going to pass these arguments to it. That is, I have no clue what they are. Two of them are possibly pointers to source and destination of the exception, and first one I have no clue. And then we are just getting a function type here that returns a void and has these arguments. Let's see what else is here. Is varag, and it is not a variable argument function. All right. So then we're creating our function. I believe this is the name here. It has external linkage, so you can call it from outside. And this is the module that we're creating the function inside, I believe. All right. Makes perfect sense so far. And then exceptional add to raise exception. Function tags. What is function tags exceptional? I believe this is revenge code. Yeah, it is revenge code. Okay, I have no clue what it does, but add to, and it takes a reference. I believe it adds a tag to this function. I'm not that familiar with LLVM IR and how tags and stuff work, so yeah. And then we have this function dispatcher. We're creating the dispatcher here. Are we? Okay, we're creating the dispatcher as a function. We have the dispatcher in the root. There's a label called dispatcher in the root function. So you at the beginning you just jump to that dispatcher. So now that we're going to have isolated functions, we need to have a function called dispatcher to call it as well. So, and then there is this tag assigned to its function dispatcher tag. I have no clue what these tags do. Hopefully I will figure it out. Then we're creating this function. The function takes it returns a void, create function type. No. Yeah, I believe void create function type. What does this do? Create function type, LLVM function. This is an LLVM code. LLVM context, create function type void, variadic false. What is the difference between this and that? I think this is just creating a function that returns void and takes void. So let's swap out correct. This is the function name. Again, we have external linkage there. Then we have function tags. So far the code that we have seen, all of this can be done on the constructor. I would really prefer it to be done on the constructor myself. Yeah, that would be safer, because if someone else is going to add some other function here, probably could run into some trouble, would have to kind of check if these are actually initialized. And you're making these pointers while you could make them normal variables, and that would ensure their existence and would avoid some kind of bug. So I'm gonna do a quick note here for these. These all can be source PC, exception destination PC. These two can be constructed at construction. And then we have not those, turn it not that even. Function dispatcher, call raise exception. We have seen these two can be done. Okay, so what my note is going to be is isolate functions.cpp line 146, because I'm trying to mention the construction. Construct everything that you can construct on construction. Every can construct every member. So we know what we're talking about. Every member on constructor of the class. Okay, that seems fair. Oopsie do. What did I do? I closed it. How do I open it? Echo notes. Right. So let's get back to where we were and continue reading. So there we are creating another function here, call maker function. This call maker function is supposed to probably make a call. Again, this can be constructed on the constructor, where we're doing it here. And what is create returning us a pointer? I'm not even checking that pointer. Since this is returning us a pointer, this may return us null pointer. And if it does so, what happens? I have no clue. I'm going to add another note here. Let's start from line 847. Return, check the return value, which is a pointer at and null. All right. Function, binary function. All right, for model function model, I believe this is not an LLVM structure either. Let's see what this is. Entry, this is a revenge structure here. It has a name, entry, meta address, entry values. This is something that we're getting from our model, which is the binary. I believe this model represents the exact binary that was the input of the revenge. So I believe this just represents the input of the revenge, and then we're iterating on the functions that was found in the input. So we have the raw format of raw model of our binary model of our input binary. So we're looking at the functions in that binary. Then what it does is type function type fake. What does that mean? Fake function, that doesn't help much. No return function, normal function, invalid entry. This is the enum. Why does this? Why is this not an enum class? Why did they try to do it like this? They have a namespace and then enum, where they could simply do enum class. So they kind of want their enum to be namespace protected, but they probably don't want it to be type safe, because this is kind of similar to enum class, but it only doesn't. The only thing that it doesn't have is the type safety. So let's do a quick note here as well. Uh, binary.h enum values. What was the line number? The line number is 858. 858. And why not simply use enum class? What is the issue with type safety? Sometimes the issue with type safety would be that you want to do some kind of mathematical operations on your enums, and enum class would require you to kind of implement your own integral functions that would integer functions that would work on your enum class. But here I don't think they're going for that, so I believe this could simply be turned into an enum class rather than simple enums. This is like pre C++ 11. I don't know where enum class has been introduced, but I would assume it is either 11 or prior to 11. So this code would be prior to 11 style of C++. Anyways, let's continue on that. So we're ignoring the fake functions, whatever those mean, and then we're isolated functions map. I have no clue what that is. First would be I. What is I? I is an integer, and then we're doing this. What is this? Where did this come from? I have no clue. Let's see what this is. Isolate function map. So it is our member. And what is the type? Isolation. So it's a map from basic block to pair of integer and function. So I think this is the list of the isolated functions. So there will be a basic block. So for each basic block inside our main function, which is the root function, we're going to isolate a function, probably. Not definitely, but probably we're going to isolate a function. So what we do is we map each of our basic blocks to the resulted function that we have extracted. So this is the counter here. As we saw, there was an I there that was counting from 0, I believe, or 1. And then there is this function that probably is going to be, yeah, the function that we have isolated at the end of the pass. All right, let's see this. Let's see where this is going. All right, so here the insertion is happening here. Right here, we are inserting by this index operator. The index operator can do an insertion if the element doesn't already exist, which I believe it doesn't, because after construction it is an empty map, and so far we have not inserted anything, so we are inserting something here. So after the insertion, it is taking the first of the pair which was an integer, and then it is indexing it from 1 to whatever. All right. So also this get block add that takes the function entry. So I believe this we're taking the functions from our binary list of our functions from binary. Then we're asking where is the entry point for this function in our lifted LLVM IR, and that is this entry here. And then we're saying that give us the block for that. So it is giving us the block for this function, and then we are mapping that function to an actual function that has an index, and later on we'll have an LLVM function inside it. All right, that makes kind of sense to me. Hopefully it does to you as well. You have quite a bit. It's been 51 minutes that we have been streaming. Let's keep this going, I guess, for a while, but I will probably go for some kind of break. Yeah, let's see how it goes. Anyways, let's continue. There's this. All right, so we're just here we have a list of functions that we are hoping to extract from our root function. Let's see what happens later. So we have a set of isolated functions here. We are iterating on our what do we on these again binary functions here, same as this. Why did we not continue what we were doing up there? No clue. Okay, anyways, that's odd. So we're simply calling isolate function, and that magically isolates our function, and then there we have an isolated function, an entry block, and then we have this get block add that we had right up there. Why are we not using this? No clue. Basic block function. I have no idea why we are not using this. Anyways, and later on we have this basic block, original entry, get block, then we have this insert that is not required. We already have it. Oh, no. We need this insert. This is something new. Okay, we're inserting there our isolated function, and then we're doing this. Okay, let me simplify this code for you a bit. You can copy this up here, move this up here. All right, isolate function. I would simply first isolate the function. I would remove this variable completely. I would insert this here, use the size here, and then this would go up here. Maybe I would do stud make pair here, do stud make pair, then that there, and isolated function here. All right, what was wrong with this? Why did they go through those groups? It works, right? And we don't need this here. Simple as it gets. Let's see what has been changed so far. Okay, I don't have this on Git because this is something that's been pulled by Orchestra. So yeah, I don't have Git for this. Maybe if I get inside and open the code there, let's see. Okay, there's this. cd orchestra sources revenge and open this code that gives me another code instance here. You guys probably are not seeing it. Do I have a git here? Yes, I do have a git here. Okay, let me do a quick change here for you guys. Orchestra isolated function. No, that is not what I'm going for. Where is the other code instance? What is wrong with you? Interesting. It is not in the list. Let me isolate functions. Let me open this up. Why is OBS trolling me today? Discord, no. Calculator, no. Git, no. Task Manager, no. Chrome, no. Explorer, no. Unity, no. What is wrong here? Okay, anyways, yeah, I'm not gonna then do share the okay, yeah, I'm not sharing that. Let me do this. Okay, yeah, you have it now. Okay, this is the final code here, and this is our changes here. So what we did is reuse this loop that we had up there. We just copied the code up here and refactored and got rid of a bunch of stuff here. So this is the insert that we had. We could make this an in place maybe even. Let me do this in place, and then we would do something like this. All right. Okay, and this could work. So let's see, let's make sure that the code that we have here actually does what the old code did. So instead of this counter I am using the size of isolated functions here. And then I am inserting each isolated function into these isolated functions. That was done here as well. And then what I'm doing here is here I have a typo there as well. Should be fine now. It's not fine. In place. Okay. So we're isolating our function, then we're inserting our function, and then we're doing an entry on this as we did here. This is doing the second of the map of the pair. We have the second of the pair here. And this I was the first of the pair. I'm using the size of our set here as the I. And then the index on the map is this get block. I have no clue why we haven't used this entry block. I believe this entry block is equal to this, but no clue why we haven't used it. We are getting it again. So that's a performance hit probably here. And why is this not a constant? These are 2 pointers here that we're getting. Anyways, yeah, this code is the exact thing that this code does. So yeah, I have no clue why they haven't done this. I'm gonna put a note here for that. Also, let me do quickly change you to window capture here. I need this stream deck for this really. Anyways, that's the code we got. Let's put a note here for it. And Isolate functions, that's CPP. What line is it? Line. Okay, let me go to the original code and check the line from there. 865. Also, I am a bit behind their Git, so probably my lines, there's a probability there that my lines are not the same as theirs. Then, yeah. And the comment would be that you can simply merge the two loops to achieve better performance. Okay, that's the comment there. And let's continue with this. Okay, and I'm on the wrong VS Code. Okay, let's get here. So this did the isolation. We have no clue how isolation was done because this is doing the isolation. This code can be removed here. And then it is replacing the call maker. We have no clue what that does. And there is this erase pattern. So why is that? No clue. Then the call maker is set to null pointer. I have no clue why. Rev.ng check, not verify module. This nut here, this nut just is really nice. This is the same as this. If you didn't know, why are they using this? Anyways, verify module, and debugs. I have no clue what that does. What is rev.ng check? I believe rev.ng check is some kind of assertion. Macro overload. Let's see what rev.ng check is. Macro overload 1 over 2. So there's an overload for rev.ng check implementation, and implementation no message. And let's go to rev.ng check with no message. Okay, we got the message one. Okay, Boolean cast what, then we get condition, and if the condition fails, we're going to fail as well, and there's going to be a message. So this is simply assertion, but I have no clue why it is so complicated here. And so if verify module fails, verify module returns false. If it returns true, what does verify module do? What is the return type of this? Return true if module is broken. Okay, that is kind of unintuitive. What is this isolate function? That's CPP line 100. Why backwards? Line 100. Why true on fail? False on fail? Okay, I guess that kind of gets the point across, I hope. Anyways, then we're checking if the function is actually correct, the modified module is actually correct, and then populate function dispatcher probably does what the name suggests. Create a function and basic blocks needed for the correct execution of the function handling mechanism. All right, whatever that means, populate the function dispatcher, which I hope does what the name says. These comments are really not necessary. These are not adding any kind of information. So this is kind of a like code smell because you're documenting whatever the exact name of the function says. So why does this actually exist? Anyways, let's move on and eliminate unreachable blocks. All right, clean up root. Before emitting it in output, we check that the module in passes. We check the module in passes. The verify module pass is here. Verify log is enabled, and then we verify module again. So I'm assuming these functions are actually modifying the module here. So that's why it is checking it every time. So we checked it again once here and again here. Anyways, that's all what the run function does. fairly simple. I guess it's not going to be as simple when we get to this isolate function that does all the magic. All right, this is the isolate function that actually does isolate our function. We have the binary function here, and I'm assuming that the binary function has access to original entry here. And let's see if the original entry is actually returned anywhere. Because I believe, yeah, the return is original entry. So we don't actually have to call the original entry here. This entry block is the same as this. The code is exactly the same. Let me do a comment there as well. Okay, let me duplicate it. Okay, let me add this. And the original entry is passed by the isolate function. Why not reuse it? All right. Okay. Let's go back to our isolate function here. So there's this old to new value to value map type. Map from original value to new ones. Okay. I have no clue what that is. And list of cloned basic blocks. Dummy entry and return block are pre-allocated. I have no clue what that is, but let's see. So there's this concept that we have and that is you only declare something when you actually need it. So this declaration can be moved down here, maybe this declaration as well. Okay, I think maybe not really, but this declaration can be moved down. And what do we do? But what is this? I have no clue. Let's read the code. Basic block creates a basic block root function and null pointer and name. So this creates a basic block, takes the name, creates the basic block, and that's it. This could be a function, maybe lambda it suffice. Anyways, it creates a return basic block and unexpected PC basic block. All right. Return block. List of cloned basic blocks, dummy entry and return block are pre-allocated. Get block add function entry, original entry, then we have, so one thing to have in mind is that isolate is actually just operating on a single function, not to be mistaken by anything else. There could be a misconception that it is actually operating on whole thing. So there's this certain function that we're trying to isolate here. So there's this return basic block for it. There is this unexpected PC basic block for the set function, and all to new unexpected PC and unexpected PC block. But what is this GCBI? Just unexpected PC. So we're going to change the unexpected PC, I believe. So that's why we have a new block for it. And that's why we have this old to new. I believe they're going to like kind of take a list of all the things that they are trying to change and then keep that somewhere and then commit it once at a time. Handle basic blocks, all to new block, clone blocks. Remap instructions in blocks, so all to new. So yeah, I believe that that is what they're trying to do here. And they're going to change the clone block, create BB, return block, create context. So I'm assuming they're creating some kind of blocks that are going to be changed. So the return block, unexpected PC block are going to be changed. All right, I can deal with that. I am going to take a quick break here and I will be back. Let me write it on the page here. Taking a quick break. Share the page window with you. Why is this not updated? All right. I hope that works. I'm gonna take a quick break and we'll be back with something to drink, hopefully. All right, I am back. Let's continue. So these are some of the blocks that we don't know what they do. I believe the return block does the prologue, and probably the unexpected PC block does some kind of error handling for the dispatcher that the PC that we are trying to jump to is not does not map to any block. Anyways, get block at that we saw a couple of times. There's our logger function entry dump logger. Uh, huh? Why? Why? How is the logger? Oh, okay. So we're dumping the entry of the function to the logger, I believe. Okay. And then there's this do log that probably yes, there's the log terminator that is flushing our log, and then there is this logger indent delogger, adding some kind of indentation to our logger. All right. Then we have this function CFG. We're getting the control flow. We have the control flow graph. We're taking blocks from our function here, and also have in mind that these basic blocks that we're talking about here are revenge basic blocks, but this basic block that we're talking here is LLVM basic block, so the namespace does matter here. So this function, which is a revenge function, we're iterating on the control flow graph of the revenge function, taking the blocks, the basic blocks, then we're doing all the logging that we are doing here. Then we have an indent, and then we have this handle basic block. Revenge insert dummy entry block. Anyways, okay, that's here's our old to new map that we're passing to this, probably going to modify it. And then we have this block that is the original block that we're going to probably modify. And then there is this cloned blocks. What is this cloned blocks? Okay, they are these to return an unexpected PC. Let's see. Let's go and see what this handle basic block does, because the rest, I believe, is not that interesting. This is the core of function isolation, I believe. Right? Here's our handle basic block. Let's see what it does. Call consumed. Set at most once. Okay, this is some kind of flag to set and know that you have set it. So this is a do once flag. We have similar things for on C++ concurrency. And this is LLVMs, I believe, or no, it is not LLVMs. What is this then? It is something here. It is in state here. Set to false. There is this set, assert not set. Then we have state equals to true. Right? Seems simple. 0, 1. I would assume these would be in some kind of infrastructure code, not in my isolate function code, but that is not the case for now. Okay. Call consumed. There's the flag. We have these boundaries. That is vector of boundaries, clone, and identify boundaries. Block start, and then alt to new is passed to it. And then there's these cloned blocks. What is the rest doing? Successor container, expected successor, block, dot successor. So these are the list of the successors to this block. So uh, when we return from this block, who can be the successor, who can be the next block that is going to be executed after this block. So we're getting the successors of this block, and then interesting. So if the destination of each block is not, each successor block is not start, why not use a better name than E? What is E? Anyways, so if there's no circularity here, what it's going to try to do is expected successor of E equals to 0. I think we need to take a look at what this successor container is. I believe it's a map. Yeah, it's a map from function age to integer. Okay. And what does that do? Clone and identify boundaries. Let's go and see what this clone and identify boundaries do. Get blocks generated by PC tree. So we have this basic blocks, list of blocks, basic block, get block generated by PC. What does that mean? Chapters. Okay, it is getting the block that has been generated. This basic block here is okay, meta address entry. Okay, I kind of understand it now. So here on our call to clone and identify boundaries, we're giving it the start address of our block, which is a revenge block, and then from that address here on clone and identify boundaries, we're getting the actual LLVM block here, and then we're placing that block inside a set of our blocks. And then we're doing some kind of revenge assert to make sure that this is larger than 0, which means we have actually found some blocks. And then there is this boundaries that we're going to extract from each basic block, I believe. So sorry, here's the basic block. For each basic block, what we're doing is we're cloning the basic block. There is the old to new BB root function. Then we're inserting that old to new basic block BB is not of size 0. Count BB is not of size 0. Okay, so we're trying to make sure that it has actually been inserted is 0. We're trying to make sure that it is not been inserted. What is this old to new value to value map type? All right. Then we're inserting it BB and new BB. But why are we passing this old to new to clone basic block? I will have to read this later. Then there's this old to new, we're inserting it BB and new BB, we're pushing back the new BB on cloned blocks here. So we're just cloning the blocks. Okay. new BB, and then we're saying that we're going to modify, we're going to put the new block in place of old block later by this. And then what we're doing here has not been cloned. Successor dot count successor is equal to 0. What does this mean? Has not been cloned. Is this a boundary basic block? Okay, okay, okay. Okay, I guess I understand what is happening here. We're checking and seeing if there are no successors here for a block, which is blocks.count successor. How does that work? Basic block successor. So if the successor of the block of some certain block does not exist in the whole blocks that we're passed here, uh, of every block that we got, if any of successors of BB has not been cloned, then we assume that is a boundary block. We're creating a boundary block for new BB. There's this callee get function call, callee BB fall through get successor BB. I need to reread this whole part, this part. I have no clue, but it's somehow extracting the boundary functions, but okay, let's do it boundary blocks, and then it is returning the boundary blocks. I'm not familiar exactly with the algorithm that they're using to do this, so I don't understand it deeply, like the whole thing is supposed to be, whole algorithm is supposed to do, but I'm kind of trying to familiarize myself with the algorithm and what the code is doing. So I kind of know, I kind of understand what it's trying to do. Anyways, all right. Other than that, let's see from where we got here. Call to this, so it was here. So we got our boundaries here, and then we're going to get the block successors here. Successor container, you'll have the list of our successors. A map from function age to successor. And then indirect count, where is this used? Nowhere. Let's put, this is literally not used, line 635. 635 unused variable. Okay. Now, if logger is enabled, we're logging. Who cares about logging? And then consume direct jump calls. Call consumed self set if result. All right. Call consumed. Why are we not putting this flag down here? I would simply move this down here. Call consumed. That's it. Consume. Let me come here and do a quick 616. Move variable to closest to first use. Call consumed. Also, what is with the code style? Why is variables capitalized? I've never seen that before. Indirect count is unused variable indirect count. Okay. Debugger is enabled. I'm gonna skip the logging here for now. And boundary, I have no clue how to actually access the log. I tried to run this code once and it crashed somewhere. So yeah, currently I'm not able to run it. I'm trying to write my own pass in the next session. So yeah, I hope I figure out where the log is after running my own code, because I want to kind of write a pass and see how things goes. Okay, then we have this for on the boundaries. If not boundary.successor.anyPC or boundary.successor.unexpected PC. So we're checking that the boundary successor is a valid successor. What is with using not and or here? These, I haven't seen any code that actually does this. This is the first time. Anyways, there is this poor result, handle direct boundary. I have no idea what that does. The name is not really that good. And then, okay, I'm assuming this is consuming a call, and it is checking if the call has been consumed, and it should only consume it once, because if you consume it the second time, this assertion inside this call consumed going to fail. To do this is obscure and confusing, as indirect boundary and call is consumed. So if call is not consumed or it doesn't have indirect boundary, we are going to fail. So either the call should be consumed or it doesn't have an indirect boundary, it has an indirect boundary. He is correct though. This is actually obscure and confusing, but I think the rest of the code is so as well. Anyways, also I would like more consts, like there could be a const here. Handle indirect boundary. So if we're handling the direct boundary, then we're handling the indirect boundary. Either of those should succeed. We should get some kind of boundaries, and then we're going to fail if we didn't get the boundary. Okay, I believe that is enough for today. I'm not going to review further this section of the code. Maybe later I will go live again and try to read more, or maybe I will just start implementing my own pass, because that's the assignment that I've been given. And yeah, I will probably do that. That way you can kind of get familiarized with the build system and setting up a pass of your own as well. So maybe if you like this kind of code, maybe you enjoy the project, you can later try to contribute to it as well. All right, I guess that's it. Thanks for watching for now, and see you later.